So I want to say a few things about pointers. So maybe you've heard of pointers before. Um, so in a computer, you can imagine that there are a whole bunch of memory addresses. Like, I don't know, how could they go? So maybe the first address is 0, and then it goes uh, 1, 2, 3, 4, 5, etc. And in these memory addresses, there are values, like a byte's worth of information. So maybe it's like 0001, 0001. So that could be the content at that memory address, and then at the next memory address, there's some other content, and maybe this one is 111, and so on like that. So there are addresses, but there are also values in the addresses. So if you let's write a program here to show how that works a little bit. If you have a variable like an integer a and it's equal to 2, if you print out a, then what it prints out is the value of a, which is 2, right? But a also has an address, and C lets you work with the address also, and so that can be useful for various things. This is how you work with the address. So there's this operator, which is the ampersand. When you put that in front of a variable, what it does is instead of talking about the variable, it talks about the address of the variable. And now I have to change this to a P because that's the formatting symbol for pointer. We've looked at this chart. I showed you the chart in the last video for the output codes, but in fact there are just hundreds of them. There are too many to memorize, but this is the one for pointer. So if we print this out, what we get to see, I didn't save it or something. What we get to see is the memory address of that character A in my computer. So a pointer is just a variable that is specialized for holding an address instead of a value. So if I declare a pointer, I can make the pointer, whoa, okay, quit. I can make the pointer point to the value in A just by uh, setting it equal to the address of A. And now, in some ways this is even better than A, because using this thing I can still modify the value. I can still modify what's in A if I want to. So you remember here you've got some memory address, but inside the memory address there's some value, and so you can make a little table even like this. So, oh, sorry, it looks terrible. Put that there. And I'm missing a semicolon, something's wrong. Da da da. Put that in there. Okay, so here you've got the address, which is this unpronounceable hex, and here is the value, which is 2. Now, to get from the pointer to the value, you use a star. The star is the dereferencing operator, and that means that I want to change the value and not the address. So if I do that, and then, then I look at A again, just do this same thing, what I'll see is that the address hasn't changed, but the value has changed, and that's because the dereference operator says change the content of this memory address to be 5 from whatever it was before. So the dereference operator undoes what the ampersand does. So if I do this, it's like they cancel each other out. So this is going to get the address, but this is going to take the address back to the thing, and the effect will be that nothing changes. This will still be 2, right? And so it can work the other way too if you want to printf, let's try to print out a pointer. So we can print out a pointer, and so it's just this, the address that we're talking about. And so you can dereference it, but then after you dereference, you can get the address, and so the effect is that they cancel each other out and nothing happens. So they're almost like algebraic inverses of each other, the dereference and the address operator. So you should be mindful that before a pointer gets assigned, it points to random junk. Let's have a look at that. So let's just say that I have I declare some end pointer a, and I don't initialize it, it just points somewhere. And let's see where it points to. So it points to, it'll be different every time you run the program, so this one points to nothing. So what if, is it the same as a null pointer? Yeah, okay, so great, it's pointing nowhere. If I try to dereference a pointer that points nowhere, or if it points to junk that I might not have the right to modify, the program will sometimes but not always blow up. And in this case it did blow up. I got something called a segmentation fault, and that's generally what happens when you try to modify some memory that you're not entitled to modify. By the way, another way to make a pointer point to that 0 value is null. That has the same effect as this. So those mean the same thing. This null value is useful. For one thing, it guarantees that it's going to explode if you try to dereference it, which is actually useful because you don't want an error to secretly happen, or happen in some kind of unreplicatable way just randomly. And also, sometimes some functions that return pointers as values, if the pointer is set to null, then it means that there was a problem. And anyway, it's kind of getting further afield. So what if you, also this is not what you want to do, right? So you might write what if you wrote that in your code? It doesn't really make any sense, and the compiler warns you about it too. It's saying, is this what you really want to do, is make the pointer point to memory location 8? So that's not it's not setting a variable equal to the value 8, it's making this thing point to the memory location 8, and then what are you going to do with that? Are you going to make memory location 8 have the value 8? So it would be cute, but it's going to blow up and give you a segmentation fault. So if you want a pointer to point somewhere meaningful, there are a couple ways to do it. One is to make it point to the address of an existing variable. So that makes sense. And then if C is 19 or something, and there's nothing wrong with that. So this is the address of the variable C, and if we looked at the value, it had value 19. Another way to make it point somewhere meaningful is to allocate memory off the heap to make it point to. And so this malloc function allocates memory off the heap to your variable, and it takes as input the number of bytes that you want to allocate. So an integer, we want this to be a pointer to an integer, and an integer is 4 bytes. So we could write 4 there. But a better thing to do is to write size of int. And the unlikely event that someday, integers are not 4 bytes, this code will still work. And so now it points to this address, which is much lower because the heap is at the top of memory. If smaller addresses are at the top and the stack is at the bottom. So this is a stack memory location, this is a heap memory location, and we're free to modify that if we want to. We own it, we can go crazy with it. We can make it 99, we can make it 98. The program will never blow up. Notice that the address changed the second time I ran it, but it's just going to change every time. Right? It's just picking up, it's being allocated a different memory address every time. And there's no rule about what memory address you're going to be assigned. So pointers can be used as arrays. What if I haven't said anything about arrays yet. So let me do times 10 here. So now instead of enough space for one int, I've allocated enough space for 10 ints. And let me fill those up with various values. For I equals 0, I less than 10, I plus plus. So let's do, there are a couple ways to do this. I'll do this using first subscript notation like this, a I equals I, and then now I'm going to write another repeat loop to print that out. So for I equals 0, I less than 10, I plus plus. Print f percent %d and a. And actually, let's look at the address too. So how about giving me a pointer? And this is nice. The second coordinate here I have to dereference. All right, and let's go. All right. Oh, and this should be this. Okay. All right. So now this shows kind of what's happened. So when I allocated 10 bytes, and this should be sorry. So when I allocated 10 bytes, I got, or actually 10 ints, it's 40 bytes. I get all these memory locations. They're right next to each other in memory, so the fancy way to say that is that they're contiguously allocated. And here I'm putting these values into these addresses. So when you do this, this is an array. It's the word for that, and you can use this sort of array notation here. So if I talk about A0, what that refers to is the 0th location here. So that is the same. I should be pointer, right? So what that is the same thing as the memory, or sorry, the value that's stored in the memory location, which is the very first memory location that is in the piece of heap memory that's has been allocated and begins there. Another way to say the same thing is this. That means the same. Actually, let's do this. This is sort of a nice exercise. So let's do for I equals 0, I less than 10, I plus plus, and I'm going to print out a truth value. Print f, and so %d will just print out the truth value, and what we'll check is that how about this, a pointer %d is equal to a pointer plus %d. And I know that might look a little bit confusing. After I run the program, though, it'll be more clear. So this first thing is just going to be the index I, and this next thing is also going to be the index I, and this is going to be the truth value. And so I'm going to check the truth of this statement, but with I plugged in for this placeholder. Okay, so this double equal sign is a comparison. So it'll return a non-zero value if this is true and a zero value if it's false. And what this is saying is that it's true every time. It's true that if I use the subscript notation over here on the left, it means the same thing as dereferencing this memory location over here. So when you combine an integer with a pointer, the system is smart enough to translate that to a memory address, which is 2 more than the memory address here, and then this dereferencer gets the value out. And so these are just two ways of saying the same thing. And when you use this approach that's described here in the second column, it's called pointer hopping. And this version is called subscript notation. And they work basically, you can do identical things with them. Sometimes you have to use this notation when you do things with void star pointers, but we won't get there for a while. So that's all I wanted to say about that.